Okay, we are going to take a look into our next unit of Chemistry 30 called Thermochemistry. So, thermochemistry is essentially just the study of energy changes by a chemical system in a chemical reaction. Now, when we talk about energy changes, we can refer to heat generally or any energy changes. Now, in thermochemistry, thermo meaning heat, okay, we're going to look at energy changes from chemical potential energy changing into chemical kinetic energy. Now, essentially, this chemical kinetic energy is just atomic or molecular kinetic energy. It's the movement of those atoms or molecules, whatever we might be looking at as an example, and how those are kinetic energy and our chemical potential energy as bonds is potential energy or a stored energy. So, some energy sources and demands. Now, obviously, in society, we require a great deal of energy usage, especially in a place like Alberta, where we need to heat our homes for a good portion of the year. So we have some energy sources. Now, we have a lot of energy sources, especially in Alberta, from fossil fuels. So we have all kinds of refining and mining to get energy from fossil fuels, and obviously we use that for things like heating, transportation, in industry, for any sort of manufacturing, commercially, anything like this. The list can go on and on and on. And generally we get this energy from fossil fuels. Now, if we are to trace all energy back, we need to know, and this is a question that is consistently brought up on diploma exams, that we need to know that all energy can be tracked back to the sun. So the source of all energy on Earth is a result of this beautiful thing, the sun. So make sure you know that. Again, the list could go on and on and on for different types of energy demands and energy sources as well. Obviously, there's other forms of renewable energy sources, such as wind, solar, and tidal energy. And obviously, we're trying to work towards creating more sustainable energy sources. But in Alberta, we definitely require and rely a great deal on this energy from fossil fuels. So, you should all be fairly familiar with this concept of the conservation of energy. Now, energy cannot be created nor destroyed. Okay, so we conserve energy. It can't be created, okay, and it can't be destroyed, but it can definitely change from one form to another. So again, we can change our energy in terms of what we're going to look at from potential energy, okay, EP, to EK, which is kinetic energy, and we can do this back and forth. Okay, so we can take a look at comparing these values of potential energy, again that's stored energy, to movement, energy of movement, or a kinetic energy. Okay, now energy is measured in joules, and in general for this chemistry unit, we're actually going to be looking at our units in kilojoules. So be sure that you're kind of keeping track of your units as we go through. Okay, so calorimetry. Now, calorimetry is essentially this first portion of this unit, and it's the process of measuring these energy changes that we have in an isolated system. Now, isolated system, again, is a system that isn't going to exchange much energy or mass to an external environment. So it's sort of a closed system, you could say. Okay, now, a calorimeter is a chemical system, and it's surrounded by a known quantity of liquid. Now, in general, this liquid is going to be water. Okay, now heat energy is transferred between the chemical system and the water. Now, when we talk about this heat energy being transferred, this heat energy can either be absorbed or released. Okay, now any energy gained is equal to any energy lost, and that's the vice versa too. We can go either way when we're looking at this. We can say any energy lost is equal to the energy gained. So if you look at my hypothetical calorimeter image on the side of my slide here, you'll see that I have this inside sort of cup that we're looking at, and this would be where your reaction takes place. Okay, now this is the actual chemical reaction portion. Okay, the piece just outside, all right, is where we have our water. Now, again, in most cases, we're dealing with water because we have to know the specific heat capacity, which we'll get to in a minute. And anything that happens in this portion of the calorimeter, we have to make sure we're using the variables that we get to calculate this portion of the calorimeter in terms of heat gain or loss. Now, the same thing goes with the reaction. We need to ensure that when we're talking about a chemical system, we're talking about the entities inside this portion of our calorimeter. Okay, so again, this energy can either be absorbed or released, but it's going to be equal amount absorbed as it is released, and that is a very, very important point to note down. I would maybe even star or highlight that in your notes. So, what I'm talking about when I'm talking about calculating our amounts from our calorimeter, okay, we're going to be looking and calculating thermal energy. And again, thermal energy is that kinetic energy of the entities of a substance. Now, kinetic energy or thermal energy is equal to Q. Now, Q is equal to mc delta T. Now, I kind of like to think of this as MCAT. That's just the easiest way for me to remember this formula, even though this delta sign isn't in fact an A. It just helps me remember. So we're talking about mass, specific heat capacity, and the change in temperature. So this is going to be the mass of our water. Okay, that is very important. It's the mass of our water. The specific heat capacity is going to be the specific heat capacity, generally of water again, okay? But this is going to be dependent on the entities in that calorimeter. But in general, it will be of water as well. And the change in temperature, again, is of the water. So notice that these three variables are referring to the outside part of our calorimeter. So if we jump back to our image here, I'm talking about any variables that affect this part is equal to Q. Okay, so anything that is changing the temperature of this water here, okay, is going to be, again, Q, and Q equals mc delta T. Now, in case you don't remember or you haven't learned this yet, specific heat capacity is essentially the quantity of energy or the amount of energy in joules required to raise the temperature of a 1 gram of water or whatever substance you're talking about, okay, by a single degree. So for water, now this value I would definitely jot down somewhere. For water, we're looking at a specific heat capacity of 4.19 joules per grams degrees Celsius. So what that means again is it takes 4.19 joules to raise 1 gram of water by 1 degree Celsius. Okay, now this value should be given to you in your chemistry data booklet. However, I would definitely be pretty familiar with it. Just make your calculations a bit faster and easier to get through. So some assumptions that we go through when we solve calorimeter problems in order for them to be sort of simplified and easier to do. Okay, these are the few that we have to consider. So energy is gained or lost by the chemical system is gained or lost by the calorimeter. So again, we have this conservation of energy. Okay, all of the material of the system is conserved. So any components or chemicals in that system are left and remain in that system. Okay, the specific heat capacity of water in dilute aqueous solutions is 4.19 joules per gram degrees Celsius. Now, dilute aqueous solutions, essentially it would be a very small amount of solute that's dissolved in water, and we just assume for simplicity's sake, because it really doesn't affect it to a certain extent, that we assume that this is still this value for dilute aqueous solutions as a specific heat capacity. Okay, the density of aqueous solutions in water is 1 gram per milliliter. So again, if density has a play in our questions, and that is what we can consider. Again, these dilute aqueous solutions, a small amount of solute doesn't affect our values enough. And the thermal energy gained or lost by a calorimeter is negligible. In other words, if there is any energy lost into the atmosphere or surrounding environment, we consider it negligible. We create a system where energy remains within that calorimeter to maintain that calculation of conservation of energy and that it's an isolated system. So we consider anything lost to the environment as negligible, or we don't need to consider it as part of our calculations. So let's take a look at trying to use this formula, Q equals mc delta T. Okay, remembering that our specific heat capacity of water is 4.19 joules per grams degrees Celsius. Okay, so it says determine the change in thermal energy, which is Q, when 115 milliliters of water is heated from 19.6 degrees Celsius to 98.8 degrees Celsius. So we have Q, which is equal to mc delta T. Okay, we have our mass. Now, 1 milliliter is equal to 1 gram. So our mass of water is 115 milliliters or grams of water. Okay, our specific heat capacity is 4.19 joules per grams degrees Celsius. And our change in temperature is from 98.8 degrees Celsius to 19.6 degrees Celsius. So this is gaining temperature. Okay, that means that this must be an exothermic. If we increase the temperature, there's some sort of heat being released from our system and absorbed by our calorimeter. So the difference between 98.8 and 19.6 should be our change in temperature is equal to 79.2 degrees Celsius. Okay. So when we plug this all into our calculation, we get Q equals 115 grams times 4.19 times by our 79.2 degrees Celsius. And when we get this value, we get 38,162.52 joules. Now again, generally when we take a look at these systems, we're dealing with kilojoules. So we would actually record this value in kilojoules, which would be approximately 38.2 kilojoules. Again, if you were going to move this decimal over, we have to move it 3 places over to the left. So we'd go 1, 2, 3. Again, then we'd round this to 38.2 kilojoules. Okay. So heat transfer and enthalpy change. So chemical systems have different forms of energy. Again, the first is being kinetic, and we have that from moving electrons, vibration of atoms connected by chemical bonds, and the rotation and translation of molecules. So essentially, it's anything that involves what you'll notice is the movement, vibration, movement, rotation, translation. So anything that involves kinetic energy is the energy of movement. Okay, now chemical systems definitely have both kinetic and potential energy. Okay, so again, we have potential energy, and this is from bonds and forces. So anything that has a chemical that's being pulled together either through the sharing of electrons or the stealing of electrons in ionic bonds, okay, or these intermolecular forces. Now remember, our intermolecular forces is London dispersion forces, dipole-dipole, and hydrogen bonding. Okay, any of these things will be considered potential chemical energy. Okay, now the total of the kinetic energy and the potential energy within a chemical system is called enthalpy. Okay, now when we look at enthalpy, we look at enthalpy generally in terms of one form of these energies in order to calculate the total enthalpy, but we can use what we know of conservation of energy to calculate this total enthalpy in a system. So enthalpy changes. Now enthalpy changes communicates the difference of enthalpy between products and reactants. So we can look at the change in enthalpy as our enthalpy of our products minus the enthalpy of our reactants. Okay, so we can look at our overall enthalpy and compare that from our products to our reactants. Now again, generally, our products will have more or less potential energy than our reactants do. So in general, we kind of look at our change in enthalpy as potential energy. So we look at our enthalpy as potential energy and our kinetic energy as heat energy. Okay, now again, heat, when we're talking about vibration of particles, we're talking about increased heat means increased vibration. Okay, and potential energy again is those stored energy in bonds. Now, because of the conservation of energy, we can state that our change in our enthalpy is equal to the change in our thermal energy, okay, or our heat transfer. So we can use what we know here to calculate a variety of things. Now again, this is sort of a visual representation of what's going on. We have, again, if we were looking at this system with zinc and hydrochloric acid, this will be a single replacement reaction, or we predict it to be a single replacement reaction, and we see that zinc is going to react with hydrochloric acid. Now, initially, we have a very high potential energy of a chemical system. So this energy on the side that we see here is potential energy. Okay, it's EP. And what we see is as this chemical reaction occurs, as the zinc is taking the place of the hydrogen, okay, and creating zinc chloride and hydrogen gas, okay, we see that the energy, the potential energy is dropping. And if you follow the red line, you'll see that the potential energy drops very, very low. Now, that's just because the bond energy of zinc and hydrochloric acid is a higher bond energy than our products. No problem, that's not a bad thing, but what we see here is their initial surroundings, okay, the kinetic energy or the temperature, essentially this is just the temperature of our surrounding water, is very low. And as the energy is being released from this chemical system, we see high potential energy. Now those bonds are broken and this energy is released and there's a decrease in our potential energy. We see an increase in our kinetic energy. We see an increase in heat and we see an increase in kinetic energy, and all of a sudden we have high kinetic energy of our surroundings. So we decrease our EP but increase our EK, and this is that conservation of energy. Okay, we have these values are going to be equal. EP is equal to EK. However, if we have a negative EP, it results in a positive EK. So that is one thing to keep in mind as we go through. So endothermic versus exothermic reactions. Now, in an exothermic reaction, we see a chemical change that produces energy. So in other words, heat is released. Okay, so when heat is released, we see an enthalpy change that is negative, which seems maybe a little bit counterintuitive. But essentially, we're losing energy, or we lose heat to our surroundings. So if you consider that as energy, the energy that was initially exothermic, which we had a great deal of potential energy, we had energy stored in those bonds, when that energy is released, it loses heat to its surroundings, meaning that it has a negative energy value. Whereas endothermic, we can say heat is required. We see that we have a lower potential energy and that we need to gain energy from the surroundings in order to have the reaction occur. So this enthalpy change is then positive. We see an increase in that potential energy. We had low potential energy initially, and we gained potential energy, and that energy came from heat from the surroundings. Okay, now these 2 points here, okay, that endothermic is equal to a positive value, and exothermic is equal to a negative value. Those points there, that is very, very important to know as we go through this unit. Okay, that's going to be something that consistently comes up, that you need to know exothermic, negative value, okay, or negative enthalpy. In other words, it's a negative change in enthalpy. And our endothermic is a positive change in enthalpy. Okay, so let's talk about another calorimetry question and what this means for enthalpy change. So what we have here is it says the temperature of 100 milliliters of water increases from 16.4 to 25.2. What's the enthalpy change? Okay, so let's take a look at how to potentially solve this. Now, there's a few steps that you need to go through in terms of logic. Okay, we know that Q equals mc delta T, and we also know that our enthalpy change is equal to Q. So I can use these two things to calculate enthalpy from my mc delta T variables. So again, my mass of water is 100 milliliters or 100 grams. Okay, and it increases in temperature from 16.4 degrees to 25.2 degrees, which is a change in temperature of 8.8 degrees Celsius. And our specific heat capacity is, again, 4.19 because we're dealing with water. So I can look at my change in enthalpy from calculating my mc delta T. So my enthalpy change is then equal to mc delta T, which is equal to 100 grams times 4.19 times my temperature change, which is 8.8 degrees Celsius, giving me a value of, if I round it and change my units to kilojoules, I get 3.69 kilojoules. Okay, now because we have this evidence gathered in our experiment here, we would actually say that this is the total energy transferred. Okay, so this is equal to energy transferred. Now, in order to record this as an enthalpy, as a delta H, we need to say that if it's a negative or positive value. We need to say if it's endo or exothermic. Well, there's a few hints. Okay, the temperature increases. Okay, the temperature goes up in temperature. Well, we know that because an exothermic reactions releases heat, that's a pretty good indication that this is exothermic. Okay, it also says it increases here, so that is very important. Because the temperature increased, we assume it is an exothermic. Exothermic, remember from the previous slide there, any exothermic reactions have a negative enthalpy. Okay, so this is going to be a negative 3.69 kilojoules as our final answer. Okay, it is important to record this as a negative value. Okay, we can take another look at an example. This says when 50 milliliters of 1 mole per liter hydrochloric acid is neutralized by 75 mils of 1 molar sodium hydroxide in a calorimeter, the temperature of the total solution changes from 20 to 25.6 degrees Celsius. It says determine the enthalpy change that occurs in this chemical system. So again, we have a few things that we need to go through in terms of logic. The first is, again, to remember that Q is equal to delta H. Therefore, our delta H is equal to mc delta T. Okay, so our mass. Now, we have to look at our total mass of our system. If we have 50 milliliters, and we're adding 75 milliliters, our total system, when we look at the temperature change, okay, is going to equal 125 milliliters or grams. Oh, I better not do that, that looks like a divide sign. Okay, we'll just leave it as milliliters. Okay, our specific heat capacity of this is 4.19, and the reason, again, that it's 4.19 is because we're dealing with dilute systems. We have 1 mole per liter of hydrochloric acid and 1 mole per liter of sodium hydroxide. Okay, and our change in temperature is from 25.6 to 20.2. So that should equal 5.4 degrees Celsius. Oops. When we go to plug this into our formula, we have 125 mils, or grams, we'll put it in grams for unit cancellation sake, times 4.19 times 5.4 degrees Celsius. When I go to plug that in and convert my units to kilojoules, I get 2.83 kilojoules. Again, because I'm looking at an enthalpy change, I see that my temperature change again increases. This tells me that this is an exothermic reaction, which means that my value is going to be negative 2.83 kilojoules of energy that was released from this system. Okay. Now, what we've talked about so far is looking at the total energy that's been released from a system. Now, we call that the enthalpy of reaction. It's the change in enthalpy refers to the entire energy change for the whole chemical system, okay, when our reactants change to products. So that's just the enthalpy of our products minus our reactants. That's essentially all we're talking about here. Now, we can talk about molar enthalpy of reaction, which is the enthalpy change per mole of a chemical. So we were, instead of looking at however much is in the system, we're going to look at it as a molar value, or per 1 mole. Okay, and we're going to say that this is at a constant pressure as well, just to be a sort of a standardized thing. Now, essentially, this molar enthalpy of reaction has a different style of formula, but it's in essence kind of the same thing that we've seen before. So what I have here is a formula that looks fairly confusing and convoluted, but it's more simple than it looks. Okay, so we essentially only have 3 variables that we are looking at. We have our change in enthalpy. Okay, now this little r just means enthalpy of this reaction. Now that little r can change to a C for combustion, it can change to an F for formation, it can be any letter that is involved with the type of reaction that we're dealing with. So again, this is just called the enthalpy change of reaction. Okay, and again, this is our entire reaction. Okay, so of all entities involved and the entire amount of entities involved. Our N, as you might remember from other units of chemistry, or at least hopefully you do, N is equal to chemical amount or moles. Okay, and then this third variable that we're dealing with is a delta RHM. Now, essentially, all that this means is, again, the change in enthalpy of a certain reaction, and this R will change again. If it's combustion, it'll be a C. If it's formation, it'll be an F. And it's the reaction enthalpy as a molar value. This little m means it's the molar enthalpy. Okay, so this is called molar enthalpy of reaction. Oops. So again, be very careful not to get confused. There's really only 3 variables involved. Okay, we have our enthalpy, our moles, and our molar enthalpy. These are the only 3 variables that are involved in this reaction. Okay, so we can look at how to potentially solve a problem like this when we're talking about the molar enthalpy of propane. So this says, predict the change in enthalpy due to combustion of 10 grams of propane used in a camp stove. The molar enthalpy of combustion of propane is negative 2043.9 kilojoules per mole. Now, what we need to do is we need to write out our formula initially. So, our formula is the change of our enthalpy for the combustion of propane. So we're looking at the change of the enthalpy for combustion times the number of moles of propane that we have, and times that also by the molar enthalpy of combustion of propane. Now the molar enthalpy of combustion of propane is the value given here, so all I have to do is solve for moles to get my change in enthalpy. Now my first step, like I said, moles is equal to my mass over my molar mass, and my mass is 10 grams. And my molar mass of propane is C3H8. So when I calculate my molar mass, if I need to do a little side calculation, I can do that if needed. I have each carbon is 12.01. I have 3 of them, and I have 8 times 1.01 for hydrogen. And this would give me a total of 44.11 grams per mole when I do this calculation here. So 3 times 12.01 and 8 times 1.01 gives me 44.11 grams per mole. So when I do this calculation, I simplify it and I get a molar value of 0.227 moles. Okay, so 2.227 moles. Now, essentially, I'm just going to plug that into my value to calculate my enthalpy. So my enthalpy of combustion for this reaction is equal to my moles times by my molar enthalpy, negative 2043.9 kilojoules per mole. So when I do my unit cancellation, I'll see that my moles will cancel out, and I'll get my answer as a result in kilojoules. Now when I go to solve this and simplify this, I get that my change in enthalpy of combustion, once I plug this in my calculator, is equal to negative 463 kilojoules. So what this is telling me is that for this reaction of 10 grams of propane, because I have less than 1 whole mole, it only equals 463 kilojoules that is being released. Now again, I'm saying it's being released because it is a negative sign, which means it's an exothermic reaction. Okay? So, let's continue on. So what does this mean when we're comparing enthalpy and calorimetry? Well, if we remember, delta H is equal to Q, okay? Now this is simply just because our potential energy is equal to our kinetic energy, and that's essentially comparing the same thing. This is just stating the conservation of energy. And we also know that Q is equal to MC delta T. And we know that delta H is equal to our moles times our molar enthalpy. So we can actually look at examples where we have our moles times our molar enthalpy, which equals our MC delta T. So this is essentially just that. Our delta H is equal to our Q. So we can just plug in any variables that we might be given into this entire equation to calculate any one of these variables. So let's take a look at an example like that. This example says, in a research lab, the combustion of 3.5 grams of ethanol in a sophisticated calorimeter causes the temperature of 3.63 liters of water to increase from 19.88 degrees Celsius to 26.18 degrees Celsius. Use this evidence to determine the molar enthalpy of combustion of ethanol. Now, if we think back to our little drawing of our calorimeter, I'll just sketch it here. Okay, we know that anything in this little pink canister is going to be our reaction. In this case, we're looking at the combustion of ethanol. Okay, now in this blue is our water. We measure the temperature change of that water using a thermometer, which is here. Okay, so when we're looking at this style of question, we need to be sure that we're looking at where these variables are in place and how we might plug them into our formula. So if I can keep this consistent, and anything that's going to be in blue is going to be anything that's to do with the change in my calorimeter water temperature. So it says 3.5 grams of ethanol. So that is not part of our water. That is the ethanol component. Okay, causes the temperature of 3.63 liters of water to increase in temperature from 19.88 degrees Celsius to 26.18 degrees Celsius. So when I go to write this down, I need to write that my mass is equal to 3.63 liters, which is equal to 3.63 kilograms, because 1 milliliter is equal to a gram, and we have liters, so that's equal to a kilogram. Okay, our C is again 4.19, oopsies, joules per grams degree Celsius. And our change in temperature is from 26.18, or pardon me, it's from 19.88 to 26.18. So our change in temperature there is 6.3 degrees Celsius. Okay, so 6.3 degrees Celsius. Okay, and we know that we have 3.5 grams of ethanol, which is in our little reaction container here. Okay, so another thing that we might need to do is calculate the moles, because when we look at our formula, we have that our moles times our molar enthalpy, okay, is equal to our MC delta T. So I have my M, I have my C, I have my delta T, and I can calculate my moles. So this is what I'm solving for. So let's just simplify our mole calculation here. I'm going to do that in pink to keep it consistent. Moles of our combustion of ethanol. Now ethanol is C2H5OH. So C2H5OH is our chemical formula. So our moles is equal to our mass, 3.50, over our molar mass of ethanol. Now, when we calculate for the molar mass of ethanol, we calculate it to be 46.08 grams per mole. Again, that's 12.01 times 2, and we have 4 H's, so we have 4 times 1.01. Oh, sorry, we have 6 H's, 6 times 1.01, and 16.00 for oxygen, giving us 46.08 grams per mole. So when I simplify this, again, if I have 3.50 divided by 46.08, that's going to equal 0.0759. We'll go with 595. We'll keep the number quite large here because we don't want to round this number until the very end. We only want to round once. So if you have a scientific calculator, either store that value or keep it up so that you can keep on using it. So when I go to simplify, if I'm solving for my molar enthalpy of formation, which I have in a green box up here, okay, I need to divide by my number of moles and divide by my number of moles. So when I simplify this, okay, I'm going to have that my molar enthalpy of combustion, so I should change this letter to a C, is equal to my MC delta T over N, which is going to equal my 3.63 kilograms, my 4.19 joules per grams degrees Celsius, my change in temperature, all divided by my 0.07595 moles. And now when I plug that all into my calculator, I should get, let's just see here. I should get this equaling 1,261.6 kilojoules, and I can also write that as, if I want to write it in megajoules, it's also equivalent to 1.26 megajoules. And because, again, I have an increase in temperature change, if I'm talking about the molar enthalpy of combustion, now, again, if I look at my unit cancellation, I can cancel out grams, I still have kilo, okay, cancel out grams, cancel out Celsius, I'm going to have kilojoules, okay, kilojoules per mole. So this is going to be kilojoules per mole, or 1.26 megajoules per mole. Now again, because we have exothermic, that means that I must have a negative value. So it's negative 1.26 megajoules, or negative 1,261.6 kilojoules per mole. Okay, again, negative, it's an exothermic reaction. So if we look at a summary here, this is our last slide, and again, this is just a very general summary of what we've covered so far in thermochemistry. Thermal energy is the kinetic energy of entities, okay, increases with temperature. Our change in thermal energy is Q in kilojoules, and it's measured by the change in temperature, again. Okay, heat is transferred always from our calorimeter to our reaction, or vice versa. Kinetic energy is energy of motion. Potential energy is bonds and forces. Our enthalpy change is a change of enthalpy at a constant temperature. And our molar enthalpy is the change of enthalpy expressed per mole. And this shouldn't be enthalpy change. This should be at a constant pressure. Okay. Now we have our endothermic change is energy and heat enters a chemical system and results in an increase in potential energy. So we have a positive H, okay, or we have a positive enthalpy. Our exothermic reactions, we have energy and heat exit a chemical system and results in a decrease in potential energy, meaning that our delta H is negative. Again, these two bottom points are, I would say, some of your most important things that you're going to take away from this lesson. Now there is a little assignment to complete this lesson to make sure that we're all good with calculating our thermal energy as Q and our change in enthalpy as delta H. So at this point, I would definitely recommend going back and pausing, recording any notes that you need to, and good luck.